Okay, so now let's do some problems associated with mole to energy bridges. We introduced the idea at the very end of the last video where if we look at a chemical reaction and from earlier in the semester, we can see mole to mole bridges. Well, any reaction that we look at also may include energy information. And we call this a thermochemical reaction. And then so what we can develop is a ratio, just like we could a mole to mole ratio, we could develop a mole to energy ratio that we could use. Okay, so what we're going to do is we're just going to kind of see how this works as a conversion factor. We're going to look at different types of problems here to get comfortable with this concept. Even though, as I keep mentioning, you guys know how to use conversion factors, and it's just an extra conversion factor. That's really all it is. So if we look at this problem right here, this is an interesting problem because we're actually not given, all right, the delta H for that reaction, and we're trying to find it. We have to find or we have to create the mole to energy bridge for this problem, okay? So if you look at the information that I give here, the reaction produces 60.5 kilojoules of energy for every 3.5 moles of A that are reacted. What is delta H for this reaction? What am I going to write aside of this reaction to make sure that it shows the correct mole to energy bridge? Well, this reaction has a 1 here in front of the A, okay? And I'm given 3.5 moles of A are associated with producing 60.5 kilojoules of energy. So what I really need to do is I need to create my mole to energy bridge and then translate it up into the reaction. So how we would handle this is we'd say, the reaction produces 60.5 kilojoules of energy. What does that word produce mean? That means it gives off that energy. If it gives off that energy, then we know that we should incorporate a negative sign to describe that energy, right? So you kind of have to look out for keywords like this. Produce means exothermic. It means that energy is given away. Now, what I'm going to do is, I know that this is really a mole to energy bridge hidden up there. I'm going to divide by the moles of A. Now I've made a mole to energy bridge that I'll be able to interpret up into this reaction. But there's still an issue. Is there a 3.5 here? No, up here there's a 1. So I actually have to do this division to come up with a number where I'll have a 1 mole of A in the denominator. And when I do this, I get minus 17.0 kilojoules per 1 mole of A. So now think about this, okay? If I come up here now, right? Is there 1 mole of A here? Yes. And is there 1 mole of A there? Yeah. So if I write minus 17.0 kilojoules here, right? Notice that what this tells me is that there's minus 17 kilojoules per 1 mole of A and minus 17 kilojoules per 2 moles of B. This is essentially the correct number there that gives me the correct ratio, right? That leads to energy information being translated to A information or energy information being translated into B information, right? Just to make sure you kind of understand why this works before we leave this example. It's a bit confusing the first time you see it. We're going to do some other examples that'll help us solidify this idea. So you might be saying to yourself, well, we haven't really talked about B at all. And how do I know this minus 17 really corresponds to B information? Well, we can make a mole to energy bridge, right, for B as well. We know from this reaction that for every 1 mole of A, there are 2 moles of B. Okay, hold on a second. Notice what we build right here. We have minus 17.0 kilojoules of energy for 2 moles of B. Come up here to this reaction. Again, if we understand and interpret those mole to energy bridges, essentially we've just proven what we had before. Because this reaction up here says that we get minus 17.0 kilojoules of energy for every 2 moles of B. And that's the mole to energy bridge that I see there. So for both those regions, from both those perspectives that we present, we see that this is the correct value for the delta H that you would write in the thermochemical reaction. Okay. Now, most of the time, all right, we actually know the delta H and we're told to use it. So this example is important because you will see problems like this, but most of the time what we're given is a delta H that we know and a known reaction. And then we're asked to analyze it. So this next example is actually from your chapter 5 PowerPoint, and it's slide number 1. And it shows an interesting process. What it shows is fluorine gas is reacted, all right? And we're breaking apart the fluorine gas into its two atoms. So remember how we view this F2. There's a covalent bond between two F atoms. And now we are going in there and ripping apart the atoms, right? And we're making two separate Fs. This requires energy. This is an endothermic process. Literally, you can kind of think about you yourself having to go in there, grab these guys and pull them apart. It takes energy to break that bond, right? Bonds are stored energy. We need to put energy in there to rip them apart. So it makes sense that this is an endothermic process. Then what the problem does is it gives us a bunch of information about F2, okay? And it says, hey, we're going to analyze a specific sample of F2, and we want to know how much energy it takes to completely convert it over to a bunch of just F atoms floating by themselves. Now, the information that they give is P, T, and V info because F2 is a gas. So I'm asked about energy, but energy shows up here. So here's the thought process. Energy relates to moles of F2. So I'm given F2 information, but what I really have here and what I really need to work towards, if I want this energy information, I need to know and be able to utilize my mole to energy bridge. Well, I'm not given moles in the problem, but am I given information that I could use to get to moles? And the answer is yes, because from our other recognition steps, when you're given a P, a T, and a V, you know that you can use the ideal gas law. And so what I can do is I can solve this for N, right, which looks like PV over RT, okay? Now, you can do this work on your own, okay? I'm going to write down what the answer is here, okay? But I want you to confirm it. Remember that this degree Celsius would have to do what? Be converted to Kelvin to get the correct answer. But what I get for the moles, all right, of F2 gas is I get 0.0408727 moles of F2. If I pay attention to significant figures, there would be 3 significant figures there. Okay. Now, how does that help us? Well, now that we have moles, our final goal is energy. And mole to energy relationships are known in these thermochemical reactions. So what I can do is I can take my 0.0408727 moles of F2. And what I see from this reaction is we need 46 kilojoules for every 1 mole of F2. My mole to energy bridge can be found by taking the delta H information and using this stoichiometric coefficient there. And so I plug this into my calculator. And remember, this energy is going to be in the form of heat, but all they asked for was energy. So we work towards that correct energy unit. And when I plug this into my calculator, what I get out is 1.8801 kilojoules. There would be 2 significant figures there because these guys are measured. And so my final answer is 1.9 kilojoules of energy. So now you can see mole to energy bridges and their uses, all right? I like this problem because it incorporates the information from the previous chapter that we just did, but just kind of think about the general process. If I need to use a mole to energy bridge, there's a ton of ways we've learned this semester to get to moles, okay? So you think about all those different processes, you have those general skills down. In this case, we have gas information, so we use it to get to moles, and then you use your bridge, and you can get that energy information back or out, right? So finally, right, we're going to do one last example together dealing with mole to energy bridges. And this next example actually involves a combustion. Okay, and this is, slide 2. So this is your chapter 5 PowerPoint. This is slide 2. Now, combustions are famous reactions. I mean, we use them in our cars. We use them whenever we burn anything, right? And essentially what we're going to do at the start of this problem is just discuss the combustion a little bit, right? Because what you're given, right, in this problem is that you are trying to combust acetylene, right? Now, acetylene is C2H2. Combustion reactions are all the same. If you think about even lighting a fire, what you need to combust something is you need oxygen as the other reactant. You then apply a spark, and you always get out the same two products. You always generate CO2 and H2O. Now, this H2O might be in a liquid form depending on the conditions of the reaction, but essentially, every combustion is the same. I need some oxygen to fuel that combustion. I provide a spark. These guys react. They turn into CO2 and H2O. Take a second to try to balance this reaction, all right? So pause the video just as a little bit of practice. Your final's coming up in a little bit of time, so it's a nice little review. Try to balance this guy. Okay. Now, when I balance this, let me use a different color. When I balance this, using whole numbers, I get a 2 here, a 5 here, a 4 here, and a 2 here. And all I'm doing is counting on the left-hand side and the right-hand side and making sure that everything is obeying the law of conservation of mass. So this looks like a combustion. If you ever see that word combustion, just remember O2 is the other reactant, right? And you get CO2 and H2O out. Okay. Now let's analyze the rest of the problem. And there's one little really important catch here. So the information that you're given is, you're given delta H for the combustion of acetylene, and you're given it as minus 1.300 times 10 to the third kilojoules. So a couple things before we start here in terms of our analysis, right? This is for the delta H of combustion, so it's for this reaction, but it's the combustion of acetylene. We do see that it's exothermic, and that makes sense because every combustion we've run into in the real world generates heat. You know, think about your engine generating heat, think about a fire generating heat, okay? Combustions generate heat, so it makes sense that it's exothermic. But an important caveat here when we look at this delta H is that this delta H is given per 1 mole of acetylene. That is just a definition. If you look up delta H's of combustion, and there'll be other delta H's that we run into later on this chapter, right? They're always per 1 mole of that thing that you're referencing. So in this case, because this was delta H of combustion for acetylene, right? This is how much energy you get per 1 mole of acetylene. And you might be saying to yourself, okay, well, that's no big deal. But remember, right? These delta H's, we write them aside of this reaction. And then we build moles and energy bridges. Well, I see a big issue here. If I and Chem 101 and your book give you this delta H of combustion per 1 mole of acetylene, this would not be the number we would write next to this reaction. Because if this is per 1 mole of acetylene, what do I see here? I see 2 moles of acetylene. So if I wrote minus 1.300 times 10 to the third next to this reaction, and then tried to rebuild this bridge, I would put a 2 down here, and then I would be getting the wrong answer, the wrong information. So it's an important concept. It's another little bit of confusion that needs a little bit of time to work out. But when you're given these delta H's of combustion, and later on, just as a preview, we're going to be given delta H's of formation, and it'll act the same way. You're given for 1 mole of that species being referenced. And if you see a different mole in the reaction, you have to either change the moles down here or change the moles in the reaction. So I'm going to show you the traditional way of doing this. This delta H of combustion is for 1 mole of acetylene, so I need to make this 1 mole. So what am I going to do to make this 1 mole? I'm going to divide it by 2. But if I divide this by 2, I have to divide every other coefficient by 2 as well. Okay? And then I'll have the correct delta H for 1 mole of acetylene. So I divide this by 2. And then to make sure I keep everything with the correct ratio, to make sure that I keep everything balanced, I'm going to divide this by 2. I'm going to divide this by 2. And I'm going to divide this by 2. Now notice that this is the energy per 1 mole of C2H2. And what do we see up here? We see the same coefficient. Now it's not there, but we know the 1 is implied. So now I know I can use this correctly because I see there's a 1 mole there and there's 1 mole there. So now this is my actual mole to energy bridge. Okay. Let's just make sure we're balanced just so I can kind of prove it to you. 2 C's, right? 2 H's. Let's count O's on this side. 1, 2, 3, 4, 5, right? Here we have 5 halves of an O2, all right? So if I had 5 halves, well, a half O2 is just 1 O, so I'd have 5 O's. So 5 O's and 5 O's means that everything is balanced. Okay? So now we can tackle the rest of this problem. All right? And what we're given is, we run this reaction, and we're asked to analyze oxygen. And focus there. And we run this reaction, and we generate 500.0 kilojoules of energy. Right? And then we measure some information about oxygen. We measure 2.00 liters of volume. I'm just going to label this as V of oxygen. We measure a temperature. That's 273.15 Kelvin. This is going to be the temperature of the oxygen at the beginning of that combustion process. Okay. And then what we're asked about is what must have been the pressure of oxygen in that chamber for the combustion. Well, here's our thought process. Whenever you start to see P's, T's, and V's related to each other, what's the first thing you write down on your paper every single time? The ideal gas law. So for this case, we have P equals nRT over V. And now we can analyze this equation and figure out what we're missing. Well, I know temperature, it's given to me. Volume's given to me. So if I'm trying to calculate pressure, the only thing that's missing is moles. Okay. Now remember, this is all with reference to oxygen. So I need to use the other information given and somehow find moles of oxygen. Well, what's the one bit of information we haven't referenced yet? The amount of energy actually produced. Wait a second. This whole entire video, the last part of last video, is all about realizing if I have energy and a balanced thermochemical reaction, then I have a pathway between energies and moles. I can use my mole to energy bridge here to find out the number of moles of oxygen. Okay, so in this acetylene combustion, where we would write this delta H aside of this reaction, right? Do you see a mole to energy relationship between the oxygen and energy? And hopefully you can see that there. So I would take my minus 500.0 kilojoules of energy. And what I would say is there's minus 1.300 times 10 to the third kilojoules of energy, right? For every, and remember, we just used the stoichiometric coefficient for our mole to mole energy bridge. So the stoichiometric coefficient here is 5 halves. So there's minus 1.300 times 10 to the third kilojoules of energy for every 5 halves moles of O2. We plug this into our calculator, and the moles of O2 that I get are 0.961538 moles of O2. Now, why am I picking O2? Remember, this delta H now is the correct delta H for this whole reaction. So we're asked to analyze O2, so I use that stoichiometric coefficient. Right. Paying attention to significant figures, it looks like there would be 4 significant figures here. This is measured, both have 4 significant figures. Now the rest is good practice for you to do, but kind of make sure you understand this extra part. We took our energy information, we found mole information, and then we answered what the question was asking us to answer. We took that mole information and we could plug here for N. We know R. We're given this T, it's already in Kelvin. We're given this volume, it's already in liters. And so please confirm my work. But what we get out with 3 significant figures, because we're limited by this volume, is 10.8 atmospheres. So I keep mentioning it, but it's important, okay? This mole to energy bridge, it's just another way sometimes to get to moles. And then anything we've done throughout the semester with respect to moles, then we can go ahead and answer a problem like we're familiar answering, okay? We can fit it into something else we've learned already. The new thing, and the thing that we have to realize, is that these delta H's written aside of a reaction generate this mole to energy relationship. And if you're given a delta H of combustion, right, delta H for any reaction, it's per 1 mole of the species being referenced. So we make sure if this is the combustion of acetylene that there's a 1 there, right? And sometimes that means we have to introduce fractions to our stoichiometric coefficients, okay? So how do we come up with these delta H's, right? What sort of experiments can we do? And that's going to be the focus of the next video, right? And the next video is going to deal with this process called calorimetry.